I'm education and application support for the Southwest area, and I'm currently in my home in Orange County, California.
All right. Fantastic. So it looks like we got a good group of people joining us, a much larger group than we've had in the past. So that's really fantastic to see. Great. It looks like some people have already found the chat window, which is great. Feel free to chat and what you want there. We also have the Q&A section where you can ask questions that Mark will kind of go through and answer them as he needs to, or maybe bring them up live so we can answer them verbally. I already see one here. Did you see a stormtrooper in the background? No, they are all actually quarantined in their quarters right now, so they shouldn't be out. Otherwise, if they are there, they won't be there for long. So if you have questions, throw them into the Q&A. Try to keep them out of the chat window, simply because there's a possibility we won't see them there. So throw them in the chat or in the Q&A, and we'll grab them. And there's also a raise hand function. And for this session, we don't really have much use for it, other than just to say, is everyone hearing me and seeing me properly now? Just go ahead and raise your hand. We get a good idea of who's all paying attention. We'll maybe ask a little bit later, because we know how webinars work. So great. Looks like we have a bunch of people chimed in. So I think maybe we should get started. Yeah? So I'm going to share my screen here. Turn that off, share my screen. And I'm going to walk away for a second and close my window because someone decided to start cutting their lawn. All right, hopefully that's a little bit better. All right, so binary theory. This is a pretty straightforward class. We will start with a little bit of math, but overall, the math is really not the important part of the session. It's really just to show you where things have kind of started from, so you have some kind of point of reference. But it's not something that you're going to have to remember on a regular basis. That's why we have array calculators to help figure these things out, because we don't have time to actually go and do this stuff on a regular basis. So the whole idea is we're going to talk about line array theory and how line arrays behave and different configurations of line arrays, and why we do why we configure the arrays the way we do. Anytime we start talking about line arrays, we actually need to go back a little bit further, and we want to talk about point sources. More specifically, we want to talk about the ideal point source. So the ideal point source is an infinitely small point in space where sound radiates out of it spherically. We all have this idea that sound, we get directionality from different frequencies based on the size of the driver creating that sound. So if a driver is, if it's 12-inch driver, you probably have pattern control down to about 1K. As the driver gets smaller, the frequency that you call pattern control gets higher. And if you get larger drivers, you get pattern to a lower frequency. Since this point is infinitely small, all frequencies are going to radiate omnidirectionally. And we want to know how that sound is changing as we double our distance from that point source. So we're going to we want to find out how much energy is on the surface of this sphere that is created, and then how that energy changes across that surface area each time we double our distance for it. So we can see on the screen, we have the area of a sphere being equal to 4 times pi times the radius squared. Well, the only thing that we're really interested in is how things are relatively changing against each other. So we can actually eliminate parts of this equation that don't change. Because remember, we only want to look at stuff that is changing. So if that's the case, I can eliminate 4, because that is going to, any value we put into R is always going to be multiplied by 4. It's not changing. So we don't really care about it. Same thing for pi. We don't really care about that because it is a constant. So now we have the area of a sphere is equivalent to the radius squared. So what this equation tells me is that every time I double my distance from my ideal point source, I'm going to be quadrupling my surface area because of this quadratic, this squaring that goes on. All right. So we want to know how much energy is on the surface area of the sphere. So let's look at 16 bits of sound energy or intensity. We almost never refer to, at least in the pro audio world, we don't talk about sound in terms of watts per meter or sound intensity. So we need to convert these 16 bits of energy into something that is more useful to us. The way we normally refer to sound is in terms of pressure or pascals. So we have this formula wheel here on the left side of the screen, and it gives us the equation that pressure in pascals is equivalent to, or is equal to, the square root of the intensity times the impedance. Well, since we're simply dealing in a theoretical world, the impedance is not going to change. We're not going from different air densities or from air to water or anything like that. So we can actually simplify this and say, get rid of the impedance. So now pressure is equal to the square root of the intensity. So if I want to convert these 16 bits of energy into pressure, I just do pressure 1 is equal to the square root of 16, which is, of course, 4. And we want to do the same thing when we double our radius at our second pressure measurement. So pressure 2 is equal to the square root of 4, which is, of course, 2. So now we have this energy, or this that is on the surface of these sections of the sphere in terms of pressure. But we often don't talk about sound in terms of pascals, in terms of, like, no one will go to you and say, how many pascals, how loud is this? Oh, it's so many pascals. That measurement is far too small. What we really want is the difference relative to a reference point, which is where we get dB SPL, for decibels or at the standard pressure level, which is reference to pascals. So we need to convert this change from the first radius to the second radius into a dB measurement. So to do that, we need an equation that is 20 log 10 times pressure 2, what we're trying to measure the change of, against pressure 1, our reference. So that ends up being 4, excuse me, not 4. Yeah, no, 4 divided by, wow, I'm having a hard time, guys. I am sorry. 2 divided by 4, which is, of course, 1/2. You can tell that quarantine is starting to affect my math skills. This is not a good sign. So we got 1/2, and if I throw my 20 log function in here, so 20 log 10, and this is now equal to minus 6 dB. So each time we double our distance from our point source, we're losing 6 dB. We're also cutting our energy in half and quadrupling our surface area, which is, I think, something that we all kind of already knew. We kind of have the idea that each time we double our distance from a point source, we lose 6 dB. Now, we can graph that out in a chart that looks like this. So we have our initial measurement at 1 meter, and then each time we double our distance, we lose 6 dB, all the way out to 32 meters distant. So if I want 100 dB at front of house, I need the point source to be generating at least 130 dB at 1 meter, because I'm going to lose that 30 dB as I get out to front of house. 32 meters, it's about 100 feet. That's generally where front of house ends up being. All right, so if we understand that, now we can go a little bit further and add a little bit more complexity to this idea. So now we're going to talk about the ideal line source. Again, if you have questions, add them to the Q&A section and we'll address them. So when we're talking about the ideal line source, we're talking about an infinitely thin line in space that stretches from one end of the universe to the other. And because it stretches from one end of the universe to the other, sound can't radiate upwards or downwards. It can only radiate outwards or in a cylindrical fashion. So, and we need to know, we want to also get the same information we had for a sphere. We want to know how much energy or how sound is changing each time we double our distance from this ideal line source. And again, we're only looking at the relative change between each doubling of distance. So we can then eliminate some of the variables in the equation you see on the screen. So first thing, I can delete height because we're dealing with one end of the universe to the other. Basically, there's no change there. Our pi is not changing and 2 not changing. So now I have the area is equivalent to the radius. So each time I double my distance from my line source, I am doubling my surface area. We take a look at those same 16 bits of sound energy. We can see that we have our first surface area with the 16 bits, and then we're simply doubling our surface area for a line source, unlike with the point source where we were quadrupling it. And we need to, again, convert this into pressure. So pressure 1 equals the square root of 16. And then, oh, go back. Pressure 2 being the square root of 8, which is 2.828. And we want to convert it to dB, so 20 log 10, pressure 2 divided by pressure 1. So 2.828 divided by 4, which ends up being 0.707. Put in our 20 log function, and we get minus 3 dB. So this is where we get the idea that a line array only loses 3 dB each time we double our distance from it. And if we graph that out, we can see that instead of losing the 30 dB as we went out to 32 meters, now we're only losing 15 dB. So again, if I need 100 dB at front of house, I only need 115 dB at 1 meter to achieve that. All right. All right, we do have a question here. Why don't we lose, I'm guessing this is referring to I guess this is the line source. Why do we lose, okay, no, I guess it's going to be point source. Why do we lose 6 dB when we double the area rather than quadruple, as 6 dB is half the level, not a quarter? If I'm reading the question right, it has to do with how we're dividing up the energy. When we, let me back up here so I can give you some visual reference here. I'm going to go to the point source and we look at the same thing at the line source. So we have this energy and we had the equation where we have the area is quadrupling the surface area each time we double our distance. So since we are quadrupling our surface area, and remember, we're only looking at the equivalent area of surface, and that's hard to read. We're only looking at one of the surface areas. So we are quartering our energy, which, given our equation, is going to be having our pressure, which is what we're really concerned about, which then translates to the -6 dB. If we, let me make sure I'm answering this again. And if we look at, and the same thing ends up being true when we start talking about the line source, because we're only doubling our surface area as opposed to quadrupling it. We only have half the energy when we quadruple it in the equivalent surface area, and that then equates down to a pressure difference. It's not, and in this case, it's not quite half because obviously we've got the 2.828. So it's hopefully that answers your question. If not, we can do some follow-up. We'll see. All right. So, all right. So we now know, which I think we all already knew, that ideal line sources lose 3 dB each time we double our distance. And ideal point sources lose 6 dB each time we double our distance. Again, we're still really dealing in the theoretical world, just the world of math. So let's translate this into how do we start considering this as we move towards the real world, start adding in frequency and real distances. So we want to talk about this idea of wave interaction and the idea of effective length of a line array. So we want to talk about wavelength. We really need to talk about how sound is propagating. So we all know that sound doesn't travel through the air like a tennis ball or a laser beam person to person. It is actually a change in pressure. You get a high pressure where a driver moves forward and creates and pushes the air that's in front of it, creating high pressure zones. And then the driver will move backwards, creating rarefaction or low pressure zones and pulling air molecules apart. And it's those changes in air pressure which our ears perceive as changes in frequency, depending on how fast those changes happen. And there is a physical quantitative distance that sound can occupy. And we often visualize that as a sine wave. So we talk about this idea of compression, a driver moving forward, or a peak in the sine wave. Low pressure, the rarefaction, or where the driver is moving backwards. And then you have this idea of completing one complete cycle. So if you're thinking about it in terms of a driver, you've got the driver at its neutral position, all the way forward at its peak, back at neutral, then all the way backward, and then back at neutral. And this is one cycle of a particular frequency. In this case, it doesn't really matter what frequency we're looking at. It's all ends up being the same. And we have this physical component to that, which we refer to as the wavelength, which is the distance a sound will travel for a given period of time. And it's going to be measured from equal parts within the wave. So it can be measured from peak to peak. It can measure from trough to trough, or any equivalent point within that sound wave. And that is going to be the measurement, a physical distance measurement of how far the sound traveled given a period of time. Usually it's in the terms of a second. So let's look at 3 different frequencies. We're going to look at 100 hertz, 200 hertz, and 400 hertz. And you can already see here that the times that 400 hertz goes through one complete cycle is significantly more than 100 hertz. So again, it's a higher frequency. So let's look at just one cycle of 100 hertz as our point of reference. So if we have 100 hertz, 200 hertz, 400 hertz playing, and they start at the same time. After 2.5 milliseconds, you're going to get through 1/4 of a wavelength at 100 hertz, or 90 degrees of its cycle. 200 hertz will have gone through 180 degrees, and 400 hertz will gone through one complete cycle, or 360 degrees. And then after 10 milliseconds, 100 hertz will have gone through one cycle. 200 hertz will have gone through 2 cycles, or 720 degrees of phase change. And 400 hertz will have gone through 4 cycles, or 1,440 degrees of phase change. All right, so let's take a look at how waves interact, because we just looked at that that phase is dependent upon the frequency. So we know this. That's what we just looked at. Every frequency has a different phase relationship to every other frequency. Let's look at a single frequency. In fact, let's look at 2 frequencies and or 2 of the same frequency and how they're going to interact together. So we have this first sine wave. And then we're going to add in a second sine wave that's in blue. And they are arriving exactly in time at our listener, or in phase, meaning that we're going to get a 6 dB boost, or doubling our amplitude when we have 2 sine waves of the same frequency arriving at the same time, no phase variance. If we change the phase relationship, add some delay to that second that second sine wave, we're going to get something less. We're going to look at, say, 20 degrees of phase difference. And we're going to get something that's less than 6 dB. If we keep changing that phase relationship, we're going to get less and less boost. And then we're going to get to a point where we're 90 degrees out of phase relative to the first sine wave, or the red sine wave. And this is where we're going to get a 3 dB boost just for having the 2 different signals. This is kind of an interesting point because nature gives us 3 dB for free, just for having 2 uncorrelated sources playing. So as an example, because D&B pays me really, really well, I've got my Audi R8. And I turn on its engine, and it's just running there, making noise. There's no coordination with it, it's just making noise. And because D&B thought I did a really good job this year, they gave me a second Audi R8. So I've got two engines running. They're not in any way coordinated, just random engine noise. Because I have two Audi R8s playing at the same time or running at the same time, I get 3 dB for free, just for having uncorrelated noise. So this is kind of an interesting point, this 90 degrees of phase variance, because if nature gives us 3 dB for free, why would I want to accept anything less when I'm adding two different signals together? Let's keep that in mind. That's going to be a criteria that we're going to look at going forward. So 90 degrees of phase variance being the equivalent of 3 dB boost. Keep that in mind. As we change the relationship between these frequencies, we start changing the phase, we start changing how they're interacting. When we get to about 120 degrees out of phase, or 120 degrees of phase variance, we get no amplitude boost. We might as well not even have that second sine wave at our listening point, where you're not getting anything additional from it. And as you start going further out of phase, you start to get to the point where you're getting into cancellation. Now at 150 degrees, we're losing 3 dB, which is probably not what we want. And then we get to a point where we are 180 degrees out of phase, or in complete cancellation, meaning that I've got a peak in one sine wave and I have a trough in another that neutralizes the relative pressure difference. So that way that's how you're getting that zero complete cancellation of the frequencies. All right. We do have a question. However, I don't have an answer. It's a question about if one V8 is 142 dB max SPL, then 3 V8 in array are 6 dB more. That's a really, really complex question, as it turns out. If we're looking at one frequency, that's going to be different. So if it's one frequency and everything's in phase, and you go one cabinet to two cabinets, you're going to get an additional 6 dB. To get another 6 dB, you have to go to 4 cabinets. But again, we're looking at just one frequency. As soon as you start getting into broadband signals, the principle is still the same, but the math gets much more complex really, really quickly. And I think we're going to be jumping into that really quickly. At least we're going to look at individual frequencies, and you'll start seeing how when you start getting all from 20 hertz to 20,000 hertz, how complex that starts to get. So maybe maybe if there's a follow-up to that, if my answer is not entirely clear, hold off for a minute, and then if you still have that question, re-ask that, and then we can maybe add a little bit more clarity. Cool. So we've talked about, in this section, we talked about how frequency is phase is frequency dependent, and how those different waves, different frequencies are going to be interacting with each other and their phase relationship to each other. So let's look at this additional idea of effective length. So what you see on the screen, we're really up close to something. We have an idea of what it could be, but we don't really know entirely. So this is kind of an analogy of when we start talking about sound, and then we'll just use it as a visual analogy. So we see what's on the screen. Yeah, we have an idea, but it's not a complete picture. As we start backing up from this picture, we start seeing more and more of it, and it becomes more clear what we're looking at. So the picture has become more effective. You can also get to a point where it becomes less effective. As you start backing up from this image, you have an idea of what it is, but it is not as useful as it used to be. Like when you could see the whole thing and you're just that right distance, you could get the perfect idea of what it is. At this small size, it's like, yeah, it's there, but meh, it's not really anything. Not really getting anything out of it. This is again an analogy of what we're going to be talking about with the idea of effective length of a line array. So we're going to take a line array, and we want to have some criteria of which to judge it. So one of the things that we want to ensure is that we really only want to lose 3 dB each time we double our distance from it. So we're moving a little bit more towards the real world rather than the ideal world. So now we have a fixed length line array, and we really only want it to lose 3 dB each time we double our distance. So we're trying to recreate the ideal line source behavior in the real world. We need to keep in mind that phase is frequency dependent, and that we want, when the same frequency from two sources arrives within a quarter of a wavelength, or 90 degrees, we want to be able to create that 3 dB boost. So these are some of the criteria that we need to keep in mind when we start evaluating how arrays behave. And the method that we use to evaluate these arrays is when we start talking about effective length. So we've got a line array, 16 cabinets deep. And then we have you floating right in the middle of the array. And you are a distance away from that array, which we're going to call our radius. And then we're going to simply draw a circle. And that's what we're going to be doing from here on out, is just looking at circles, drawing a bunch of circles. So let's look at what the effective length is for a given frequency. So what we want to do is let's look at 10 kilohertz. And I'm going to add on 1/4 of a wavelength at 10K to the end of my radius to the array. And you can see that on the left-hand side of the screen. And then I'm just going to draw another circle. So any cabinets on the inside of this circle any sound that's generated from them are going to be arriving at you, the listener, within 90 degrees. So within that 3 dB. So you're going to get at least a 3 dB boost from all of these cabinets contributing together. And this is what we call the effective length of the line array at 10 kilohertz. If we look at another frequency, say 1K, 1 kilohertz, we're going to do the same thing. We're going to take 1/4 of the wavelength and add it onto our radius. You can see that done on the left-hand side of the screen. And then we're going to draw another circle. And you can see that it's encompassing more of the line array. So 1K is a lower frequency than 10K. So larger wavelengths, more cabinets are interacting together. And they are arriving at the listener, at our measurement point, within the 90 degrees of phase shift. And that is the effective length at 1K. If we go even lower in frequency, we go to 100 hertz. We're going to do the same thing. We're going to extend our radius out, which you'll see on the left-hand side of the screen, and then draw a circle. And in this case, the entire array is inside of that circle. So that our entire array is effective. And every cabinet is arriving at our measurement point within that 90-degree phase shift. And that is the effective length at 100 hertz. So what we're looking at here is that depending on the frequency, we're going to be listening to more or less of the array. And the question then becomes, how does that translate into our ideal line array-like behavior? So let's take a look at different line array configurations and how they're going to benefit us. Again, if you guys have any questions, the Q&A section down below on your the menu window bar, if you have any questions, and otherwise we will move on. I'll give you a quick second. I know typing is certainly not as fast as simply raising a hand and asking a question in person. All right, so let's talk about different line array configurations. The first one we want to look at is a straight array. Now, we don't use straight arrays all that often in pro audio world. It happens from time to time, but it doesn't happen all that often. But we can, it can does it, and does have some benefits. So let's take a look. Let's do the same thing we just looked at, but let's look at it in terms of real length and real distances from the array. So we're going to get a straight array, and we're going to be floating midair right in front of the array. Now I've got, in this case, I've got 16 cabinets again, but in this case, though, the line length of this is 4.9 meters. And now we're going to be floating midair right in the middle of the array. So at 4 meters, the effective length at 100 hertz is the entire array. Again, we drew a radius, we had 4 meters from the array back to our measurement point, and then we added on the wavelength at 100 hertz onto that radius, and then simply drew a circle, and it encompassed the entire array. If we look at 1 kilohertz, we can see that we're listening to a smaller portion of the array. We drew that radius to the center and then extended for that 1/4 wavelength at 1K. So now we're listening to a smaller portion. And then we can look at 10K. And if we see 10K is a smaller portion still. All right, so that's at 4 meters. Let's double our distance from the array. As we double our distance, you can see the absolute amount of line length that we have, or the effective length at a given frequency, and also how much more of the array we're listening to. So at 100 hertz, there was no more array to listen to, so that we had no growth. But at 1K, we got about a 0.7 meter increase. And at 10K, we got 0.2 meters. Pretty significant growth. So that's great. Let's go and look at 16 meters. Double our distance again. Again, we're getting growth at 1K and 10K. We double our distance again. Again, growth. However, if I look at the picture and I also look at my numbers, I can see that my line length, effective length for 1K is 4.6 meters. I don't have that much more line length to grow when I double my distance again out to 64 meters. But at 10K, I still have plenty of growth. And at 64 meters, we get to a point where 1K is completely effective. So is 100 hertz. And we still have some growth at 10K. So what does this actually mean? because you're not going to keep this all in your head. So we've got a graph to show you how this actually looks. So each color represents a different frequency. And you can see for 100 hertz, each time we double our distance from the array, we lose 6 dB. However, for 1K and 10K, each time we double our distance, we're only losing 3 dB. So we're getting that ideal line array behavior for those higher frequencies until we get to that 32 to 64 jump for 1K, where we are now losing 3 dB. We're using the 6 dB. And remember, we weren't able to increase the amount of array proportionally enough to get that, to maintain that 3 dB loss. So let's take a look at why that matters. All right, so we lose each time. Let's look at how we are growing. So going from 4 meters to 8 meters, I am increasing the overall line length at 100 hertz by a factor of 1, so nothing. 1 times anything is the same thing. But at 1K and 10K, I'm increasing by 1.4. If I make that same doubling from 8 meters to 16 meters, I can maintain that 1.4 increase. Go out to 32 meters. Great, I'm maintaining that relationship. And then going out to 64 meters, I suddenly don't have that 1.4 because remember, we didn't have any more cabinets to listen to. So now I'm not getting that 1.4 boost. What this really translates to is to this 1.4 is really a 3 dB boost. If we go all the way back when we're talking about the ideal line source, and we're doubling our distance from the array, and we're getting that minus 3 dB, where it was 7.07. I know going into the math that I told you it wasn't all that important. If you were to reverse the values, or reverse, instead of doubling our distance from the array, if we were halving our distance, you reverse the equation, it ends up being 1.414, which is the equivalent of 3 dB boost. So what we're really getting when we're talking about effective length is that each individual cabinet is losing 6 dB. But because we're listening to 1.4 times more line length, or plus 3 dB, we're getting 3 dB more. So we're losing 6 dB in order to gain 3 dB more, based on how much more of the line array we can listen to. Hopefully that makes sense. Mark, do we have any questions that I can chime in on?
Yeah, there's a couple here about the formula of the straight array, but also, asking, are they only listening to those boxes for the frequencies? Does that mean that the other boxes are canceling out?
That's an interesting observation. So we talked about, I'm going to go back to here, and I'll continue the animation. So the question is, everything inside of this circle is adding, it's getting that 3 dB boost. And as we looked at earlier, once you get past 120 degrees, you start getting to a null point. So if we were to draw a circle to create whatever the wavelength distance is for 120 degrees of phase shift, then you would get no addition. And then at some point you would get into cancellation. But then you get into a point where you get growing addition. You keep so you get very quickly, you add on, yes, these are all contributing. And then it gets to, oh, I'm not contributing as much, and then into cancellation. And then very quickly, but a very small amount, it starts getting into, okay, now I'm adding up again. And it keeps going towards back towards that 90-degree phase shift. When you start talking about lower frequencies, you're pretty much, as we saw here, the chances of you getting into a point of cancellation is small. However, in higher frequencies, yeah, you can get to a point where you're getting some cancellation. But in general, it doesn't tend to cancel out all of the benefits that you get from that minimum of 3 dB. Remember, some of them are going to be getting a 6 dB boost. And it's anywhere between that plus 6 dB and plus 3 dB. We simply said 3 dB is our bare minimum that we want. So yes, you're getting some cancellation, but you're getting more addition than you are getting cancellation. Hopefully that answers that question or group of questions from what it seems to be. What other questions we got here? Okay, we've answered that.
The bottom one of any formula of how we get the 4.9 meters for 100 hertz, or is it complex math equation?
How we get 4.9? Well, no, that's it's not that complex at all. So I can actually do it. It's really what's the best way to look at this? It really is. It's a function of, when we say it's not 4.9 meters is 100 hertz. It's a function of the distance of our listener or a measurement point to the array and the size of the array. So there is no direct one-to-one relationship of 100 hertz and 4.9 meters. The only way that they are connected at this point is based on the position at 4 meters, and based on that distance plus 1/4 of the wavelength of 100 hertz, creating a circle that completely encompasses the array. So it's not really complex math. I mean, you can do a quick calculation. I don't know it off the top of my head, but figure out what, and you can do it for any frequency. Figure out what its quarter wavelength is, and then you can then add that onto whatever distance you are from an array, and you can see what your effective length is. Now remember, we're just dealing with a straight array here. So this is actually the least complex that we're going to get. It's only going to get more complex from here, or we're going to add little more wrinkles to it. It's not really that much more complex. All the ideas translate, but there are a couple little wrinkles that happen. But we'll get there in a minute as we start looking at different configurations of the array. Seems like there's a lot of questions coming in fast and furious here. I'm going to clarify. So what is the 1.4 more line array? Let me go backwards because I think I skipped this. In fact, I know I skipped it, but I can maybe add some clarity in here. So we're going all the way back here, where we talk about this is our doubling our distance. So this is doubling, or maybe a better way of looking at this is walking away from our distance, or not from our array, or doubling our distance. We can say we're going to move closer to the array. So I can say 20 log 10, our first radius, which is what we're going to want to reference against, and then our reference, our second double a distance. So I just reversed the values that I put into this equation here. This ends up being 1.414, which is, once you put into the 20 log function, this ends up being plus 3 dB. So we talk, we're looking at 1.4, not meters more, 1.4 times more array. So if I go back to our thing here, I'll go through. Each time we double our distance, if we can maintain that 1.4 times more line length, or another way of looking at it is 40% more line length. If we can maintain that, we get that 3 dB boost. Oh, of course I go a step too far. So hopefully that answers that question. So for clarity, when we're looking at 100 hertz, we're saying that everything within this circle, so the question is at 4 meters, saying the top box is arriving exactly 90 degrees behind the center box at 100 hertz. What we're saying is that anything that is within this circle is arriving at least 90 degrees of phase shift, or at most 90 degrees of phase shift at 4 meters. So more than likely, those outer boxes are arriving within, at 90 degrees or somewhere a little bit less than that. As you move towards the center, yeah, you're going to be closer to in phase. But remember, that's comparing like this cabinet to that cabinet. But this cabinet and this cabinet are arriving at this year in very little phase difference. So it becomes much more complex. Remember, we're looking at the entire, we're thinking about it as in the entire array. So at least you're going to be arriving within, or at most 90 degrees of phase difference. All right. Hopefully that has added some clarity, I hope. We'll see. If not, again, ask the questions. We're more than happy to answer them. And if I haven't answered it properly, let me know, and we'll add some additional clarity to them. So we looked at a straight array, and we're looking at a straight array. One of the things that we notice is that it's very good at throwing sound great distances, depending on the size of the array. As we can see for 100 hertz, it's not very good at throwing great distances. But for 1K, it's not bad up until about 32 meters, and at 10K, it's great. So straight arrays are really good for large distances. However, they're not particularly great at things up close, because as you start getting underneath of the array, you're very quickly, or if you're not directly on axis, you start getting to be out of the coverage pattern. So let's look at a variation on that. Let's look at a tightly curved array. In this case, we have 6 degrees of splay between each cabinet. Let's do the same thing we did. Look for the effective length at the 3 frequencies, but we're going to add in a wrinkle. In that we're not going to be floating midair anymore. We are now on the ground. So when we double our distance, we're doubling our ground distance. So in that case, I have measured from the front of my array straight down, and then this distance here is this distance here is my ground distance, let's say starting at 4 meters. We also have, let's see if this will show up. We also are dealing with a radius from a listener to the center of the array. And that's going to be another thing that we have to take into consideration. So we've got this tightly curved array, and we can see that at 4 meters on the ground, with a radius of 10.93 meters, we are not listening to the entire array, which is great, meaning that we have a place to grow. So let's double our distance from 4 meters to 8 meters. As we do that, we can see that we got a little bit of growth at 1K, no growth at 10K, but we're listening to more at 100 hertz. Great. Let's double our distance again. So again, okay, 60 meters, now we're losing line length due to the curvature of the array. But we are also getting minuscule amount of growth at 1K and a very small amount of growth at 10K. Let's double our distance again. Again, now we're losing more length at 100 hertz because of the curvature, and again, only small growth at 1K and 10K. And then again, 1K and 10K, again, small amounts of growth when we're doubling our distance from 32 to 64 meters. So how do we graph this? How does it look like when we graph this out? Cool. So we're looking at this. What am I seeing here? I'm seeing that up front for each frequencies, I'm actually losing less than 3 dB in that 4 to 8 meter jump. And I start losing for 1K and 10K, I'm starting to lose just about 6 dB each time I double my distance. And it gets that equivalent all the way back. So what are we seeing here? We're saying that this tightly curved array is really good for things up front, but as we move further back into a room, this is behaving like a point source. We're losing 6 dB each time we double our distance, which is not ideal. We want to go towards ideal line array behavior, so less than 6 dB each time we double our distance. So up front, this is great. Further distances, not so much. All right, let's take a look. So we know that a straight array is good for far throw applications, and we know that a tightly curved array is good for the areas right up front. Let's look at a variance on that configuration. So let's look at a less curved array, a lightly curved array. And in this case, we have 3 degrees display between each cabinet. So if we look at this again, we're going to do the same thing. We'll start at 4 meters, and immediately, just on the graphic, I could see that I'm probably out of the coverage pattern of this array. We're listening to, you can see it in the red here. We're listening to a minuscule amount of the overall line length at 10K. So let's double our distance from it and see what we got. Great. Now we're actually listening to a portion of the cabinet. Let's double our distance again. Greater portion of the array. Get increases at each frequency, which is great. Let's go to 32 meters. All right, 32 meters. Again, still getting growth, though at 100 hertz, it's not all that much. So we're probably going to start losing line length when we make this next jump from 32 to 64 meters. And we did lose line length, mainly because of the curvature of the array. and we get some growth at 1K and 10K. If we graph that out, we can see that that front area, not particularly great. We were outside of the coverage area of the array. So this lightly curved array is not really good for close-up areas. However, as we look towards this middle section here, we can see that jump from 8 meters, that 8 meters to 16 meters is actually quite good. You get a little bit of getting this boost at 1K, and that's going to be a function of our distance from the array. But overall, it's not bad. We're getting more line array-like behavior. And then as soon as you get beyond that 16-meter jump, now you're starting to lose the 6 dB each time we double our distance. So not really great for far throw applications. So if we were to compare these different arrays, knowing that with a straight array, it's really good for far throw applications. For the tightly curved array, they're really good for the front portion of the audience area. And this lightly curved array is for the mid portion of the audience area. That gives us an idea of how we could blend these different ideas together. And that's where we get the idea of the J-shaped array. Before I move on, Mark, are there any questions relating to these topics that that we just talked about that we can answer?
Yeah, one is the center of the aiming wedge is centered off the box pointed most on axis to your position, correct?
Yeah, that's correct. It's a little harder to see, but let me bring up, there's not a great way to visualize it, but let me bring up just one image here. Yeah, so what we did to generate this, to generate the graphs, we did the math was relative, that was all done in Excel to figure out what these exact numbers were. But really what we did is we just had we developed a curvature array in ArrayCalc, and then we took it into a modeling application like SketchUp or something, and simply put different measurements and then just drew a circle to the point where you get the first tangent line. So it's basically, so that's on axis center point that you're seeing right here or right here. That is going to be the first portion where that first radius, before we added on the different frequency lengths, that's the point where our radius first impacts the array. I know that's getting a little bit more mathy, but yes, the short answer, yes, that's how we got there.
Another question is there a specific type or way we can calculate the results of gain shading? Which I know it's something DMB doesn't recommend doing, so, but I don't know if there's a calculation for that.
I'm
sure there is.
I don't know of any great way to calculate gain shading. Mark is right. DNB definitely. Now this gets to the there's the sound engineer, audio purist of you never gain shade an array, and then there's the oh well, the real world happens, so sometimes you got to gain shade the array. DNB will always lean towards don't shade the array unless you absolutely have to, because there is that situation where you have up front it's a little too much, so you may have to turn it down by a dB or two. Life happens, you deal with it. However, DNB does have a solution for that where you don't have to do gain shading, which is array processing, which we do have a webinar session about array processing. If you want more information on that, there's also a really good video on our website that explains it pretty well. But the idea is that you don't have to do gain shading because it starts affecting how the entire array behaves. It's not just those bottom cabinets. It affects the entire array and how it's interacting with each other. And that is predictable, but if to quote the guys who developed array processing, it's 40-dimensional math. So I don't really have time for that or know how to do it. So I rely on calculators to help me figure that out. All right, other questions?
Another one is the line array needs to be designed so that when you double the distance, you need to fall into the coverage of an additional 1.5 times the amount of speakers at a given location that are 90 degrees in phase to keep the minus 3 dB loss. And I think you talked about this a little bit more going in the J.
We do talk about this more, but yes, in the very broad picture, you're trying to maintain. You want to get each time you double a distance, you want to maintain that 1.4 times more line length you're listening to. Not necessarily 1 times more cabinets, more about line length. Because remember, we're trying to create a coherent line array. It's not really, we have to do individual cabinets because that's just reality that we live in, but we want them to behave as if they were one unit. So if we can listen to 1.4 times more line length, we'll maintain that 3 dB loss each time we double our distance. That is the overall goal. Yes, you are absolutely correct.
Yeah, another one, in the 6 degree splays example, there is only 3 dB loss at 4 meters. So can we say that a curved array behaves like a straight array when you are close to it?
I don't know that I would say it behaves like a straight array, but I would say that it behaves more like the ideal line array. I know that's picking hairs. I know it. So yes, it's behaving like a straight array at far distances because a straight array is behaving more like an ideal line source. I know, again, picking hairs, big geek. What do you want?
Yep.
So,
all right,
cool.
I think we're good.
Okay, great. So we talked about a straight array and how it's great at throwing sound great distances. And we talked about a tightly curved array, which is great for stuff up close, and the 3 degree curved array, which is great for that mid-section area. And we want to put all these together, which is where we get this idea of the J-shaped array, which is what you guys are already doing. I'm sure every array that you have put up, or the vast majority of the arrays that you have deployed, are in this J-shaped, meaning that they're mostly straight towards the top and they gently curve to a tighter and tighter curve as you get towards the bottom of the array. So let's take a look at how that behaves. All right, so we got our J-shaped array at 4 meters, and we can see that we're listening to a good portion of the array. One of the things I could tell you to keep an eye on is keep an eye on how the signal, this moves up the array into the different sections as we keep doubling our distance, into that from the tightly curved to the lightly curved to the mostly straight. So we've got our J-shaped array at 4 meters, listening to a good portion of the array. And each time we double our distance, we're going from 4 meters to 8 meters, we're getting some growth in line length. And we keep getting that growth when we go from 8 meters to 16 meters. And going from 16 to 32 meters, we're still getting growth at 100 hertz. We're probably getting to that point where it's no longer behaving like the ideal line array. We don't have enough cabinets to listen to maintain that pattern control, to maintain that 3 dB loss. But we'll look at that when we look at the graph. And then when we go into 32 meters, lo and behold, we're definitely losing line length at 64 meters. But we're gaining everywhere else, so that's good. And we also noticed how that tangent, that circle, as we moved further from the array, as it moved up the array into the different portions of the array. So we take advantage of different behaviors. So if we look at that, let's look at that graphed out. We can see that for all the frequencies up to about 64 meters, we're maintaining ideal line array-like behavior. And what we're also doing is we're maintaining tonality in that the frequency response, and it's dropping off at a similar rate, meaning that we're getting even tonality all the way out to 16 meters. And it's not until that point where 100 hertz starts falling off. But 10K and 1K still fall off at relatively the same rate, meaning that the tonal balance stays consistent. Why does that matter? For your audience, it means that everyone is going to get the same show, regardless of where they are in the audience, at least for your high frequencies and your mid frequencies. For you, it makes optimizing the system a heck of a lot easier, because you can put in a microphone or two, take measurements, and optimize the system, and know that the changes you make on the entire array are going to be consistent across the entire listening plane. So remember, one of the goals for line array deployment is even tonality across all the listening planes. You want to make sure the audience gets the best possible show they can, and regardless of where they're sitting. So even tonality is really, really a goal here, regardless of how you go about doing it. And we can see that at 100 hertz, our line length may not be long enough to throw low frequencies that far. I feel like we've all heard this. You go to the back of an arena, back of a stadium, and there's just, the low end is just not there. Unless someone has that's why you're going to put up delays, either delay line arrays or delay subs, so you can get all of those things, all that frequency response a little bit further out into the audience area. All right. Looks like we don't have any questions. Is that correct, Mark? I don't have all my windows open, unfortunately.
No, that's correct. But we've been getting something like viewing this, the AP graph and array calc now makes more sense. Somebody commented.
Yeah, absolutely.
So that is great.
That's a really good thing. I'm glad you made a connection to that. For everyone who's not familiar, array processing is a tool that's built into array calc and our amplifiers that allows us to more evenly distribute the frequency response of a line array, even better than just the traditional configuration, physical configuration of the array. I don't want to go too much into that because it goes down a whole other rabbit hole, which we don't really have time for. But
yeah, we had a question about that earlier, but I said that we do have a couple other webinars that do go into it a little bit more. So if we don't have time for specific questions on that, maybe those webinars would be a good choice.
Yeah, so if you are, we have the currently running, there should be an array processing webinar that is being produced by our colleagues over in Backnang in Germany. And we also have the SL series introduction, which also talks about array processing to a small degree, but it's definitely there. And I believe the Making Decisions in Array Calc also touches on array processing. Again, not in super depth, but if you get those guys talking, they'll just keep on going. So so great. I'm glad you're able to make that connect. They were able to make the connection between line array like behavior, ideal line behavior, and array processing, because that's really what we're going for here. All right. So great. So we looked at why we do a J-shaped array, why we've done it forever. So let's take a look at some of the criteria that we need to talk about, or that we as a manufacturer need to consider when we're designing the cabinets. These aren't really things that you guys as system engineers, people who are deploying the system, planning the system, you don't really have to take these things into account because we're doing it. And we provide calculation systems to help you figure this stuff out, because it gets really complex really quickly. But we can at least talk about some of the criteria that we need to think about of why the individual line array cabinets, the elements, are designed in the way that they are. Because we don't have this ability to create a 4.9 meter line array that is completely variable. We have to build this as discrete components. We can't, it's not just one unit, even though we want it to behave like one unit. So let's talk about some of the criteria that we have to consider. The first one is our center-to-center spacing for low frequency elements or omnidirectional elements, where you're not getting much pattern control out of the driver itself, because we're dealing with smaller drivers, 12, 8, 10, 12, maybe 15-inch drivers. Their pattern control doesn't go all that low. So we need to have them interact with each other. So we need to take the consideration of their center-to-center distance. So if their center-to-center distance is greater than half a wavelength, whatever frequency you're looking at, you're going to get low frequency lobing. And if they are less than half a wavelength apart, we're going to get summation or narrowing. So you get all the energy focused forward, and you essentially are getting pattern control. So I think we've all experienced this greater than half a wavelength in some way or another, not necessarily in a line array, but think about your left-right sub deployments. If they're, and they generally are, greater than half a wavelength of the frequencies they're producing, you always get that power alley down the center, and then you get some lobing and troughing as you move away from that center. So for lower frequencies, it's easy to get the center-to-center spacing to be 1.7, or the half the wavelength. So if talking about 100 hertz, 1.7 meters center-to-center spacing. That's really easy to do. And as you start going lower in frequencies, that becomes larger and larger numbers. So that's easy for us to do. When you start getting into higher frequencies, 0.34 meters or 3.4 centimeters, getting that center-to-center distance with drivers that are powerful enough to actually be able to produce the SPL that we want for pro audio applications gets incredibly difficult. Center-to-center spacing at 1.7 centimeters is hard, and the drivers are exceptionally small. Possible to make them, sure, but they're not exceptionally loud and not really good for our application. So we need to find another way around the center-to-center spacing, because it doesn't work for high frequencies.
Got a question that popped up in the chat window. Are 1K and 10K WL the wrong way around on your graph?
Are they the wrong way around? 1K and 10K? Shouldn't be. Remember, we're looking at meters and centimeters. All right, it looks like.
Cool. I think that's probably.
Very good. Yeah, don't get me wrong. There have been, if this presentation alone, discoveries have been made. We're like, oh, I've been saying this wrong. Ooh, let's make a correction. So absolutely good for keeping an eye out there, folks. I really appreciate that, because it keeps me honest. So great. So we have to take a look at something else for high frequencies. And then we want to start talking about horns and waveguides. So what we want, the criteria we have to consider here, so we've got a high frequency diaphragm, and then we've got a horn attached to that. And one thing we have to look at is the curvature of the wavefront that's coming out of the horn. And really, we want to look at the difference between the curvature of the wavefront and the front of the horn. If the difference between those is greater than a quarter of the wavelength, whatever frequency we're looking at, you're going to get high frequency lobing. However, if it's less than a quarter wavelength, we get narrowing, or we get more pattern control. Why is this the criteria we're looking at? So if we look at a horn, we've got the horn, and then we've got this curvature of the wavefront coming out of it, based on the energy coming down the center of the throat of that horn, and the energy coming down the flared edge of the horn. And then if we were to take, like, let's put point sources together. Let's just put a bunch of point sources and call it a line array. There's a reason we don't do that. We've got, each one of them has the same curvature. So if we just look at the curvature of these different horns, with a single horn, you get it radiating outward like this. And then you have the second horn. And then you get this area in between where you're going to start getting real nasty comb filtering that you probably don't want. So what we're trying to do with that, the delta difference between the front of the horn and the wavefront, is we're trying to minimize this, trying to minimize the interaction to only the things that we want them to interact in. So we want that delta difference to be reduced. So we want to go from something like this into something that is more flat or completely flat. We'll look at that. So we need to able to, if we're trying to flatten out the wave, and we get the reason we have that wave curvature is because of the time difference between the energy coming off the side versus the energy coming down the center. The energy coming down the center is exiting the horn before the stuff coming down the side, therefore creating the curvature. So how do we shrink that? We simply need to increase its path length or delay it in some fashion. And we know that we can't put some digital delay on the center of that driver, center of the diaphragm. That's just not how delay works. So we need to do something else. We essentially create a path lengthening device or a waveguide. We increase the time it takes for the sound to exit out the center versus exiting out the edges of the horn. So this is the idea of a waveguide. And every manufacturer has a different flavor on it. The first waveguide that when we're talking about line arrays, the way we're thinking about them right now, was from L Acoustics in their VDOS, where it might be a little hard to see on this graph, but you have your diaphragm at the back here, and then energy, you've got this cone in the center, pointed towards the center of the diaphragm. So the energy is forced along the edge of the cone and along the edge of this waveguide or the horn. And then it comes down to this chiseled portion and it starts to be flattened out so that it can exit this narrow opening at the front of the waveguide. And at that point, then we're attaching a horn, which doesn't affect the wave coming out of in the vertical component, but we're trying to affect the horizontal component once it gets into the horn portion. D&B's first line array was the Q series with the Q1, and this is using what's called a toroidal waveguide. You know, great for those, you know, great party conversation, toroidal waveguides. And in this case, you've got, it's easy to see on this side, you've got this hump right in the center, and it comes down. What's harder to see is that there's a corresponding divot on the other side. And that divot ends up being egg-shaped, so that there is greater change towards the center and less change towards the edges. So again, increasing the path length towards the center and not increasing it as much towards the outer edge until it gets into, then it gets into the horn, which then affects the horizontal component and doesn't affect the vertical component. At least that's the design goal. And then we also have the C3, which is another waveguide style, which is actually very similar to the waveguides we use in almost all of our line arrays at this point. In this case, you can see we have this chiseled area in the center, this so-called sledgehammer design, where we're simply just cutting out the center of this waveguide and forcing energy down the top and bottom, and then pushing it out into a horn. Now, this was, of course, used on the C3, but design, go back. We had design variants on this, which are used in the J series, V series, Y series. No, Siri, you're not helping me right now. T series, the 10AL, which is our install cabinet, as well as GSL, and KSL. All use a variation on this sledgehammer design based on number of drivers, the available cabinet space, what have you. You have the JBL design, which is really a function of the length of the horn, is how they're flattening things out. As best I can tell, there's not actually much information on JBL's waveguides, unfortunately. And Eevee, one of their waveguides is actually pretty easy to understand what's going on. You've got these different path lengths in the center that are longer than the ones out to the side. So again, increasing the path length that the center energy has to travel in order to flatten out a wavefront. We all have these different waveguide designs because each one of us have patents on every design and we don't share any of our ideas. But in the end, they're all doing the same thing. They're trying to flatten out a wavefront. Then the question becomes, how flat does that wavefront need to be? So if you had a perfectly flat wavefront and you had a perfectly flat array, no splay angles between the cabinets, you would get very strong vertical pattern control. You could throw sound very, very far. However, a flat array with a slight curve to that wavefront, it's not going to be as tight a pattern control. You're going to start getting some lobing, as you can see in the graph on the right-hand side. However, generally, we're not dealing with perfectly flat arrays on a regular basis. So maybe maybe a perfectly flat wavefront isn't the solution. If we had curvature to a cabinet that had a perfectly flat wavefront, you start getting this very tight beam of energy that becomes not connected to the other cabinets. So you're not getting this connectedness between the arrays. And we want these cabinets to interact in some fashion. Whereas if you have a slight curve to that wavefront, when you add curvature to the array, they interact in a more coherent fashion, creating a consistent wave out of the entire array, creating a more consistent dispersion, as you can see on the polar plot on the right-hand side of the screen. So it's really just a matter of what are your goals end up being. Again, more party trivia. The greater the splay angle you have between cabinets, the more likely it is you're going to have a greater curvature to that wavefront. So splay angles of like 0 to 7 degrees is going to have a flatter wavefront than cabinets that have splay angles that go out to 10 or 14 degrees, which will probably have more curvature to the wavefront. All right, so considerations on the different elements within an array. What questions do you guys have? Mark, I briefly glanced over there. It seemed like there was a very long question there, and hopefully you can distill that down.
Yes, it's long. The question, it does have to do with AP, but also talking about LF coverage. So here we go. Let's try to minimize this the best I can. Problem is with low and low mid directivity beam, which is something that must be matched with super tight controlled HF, which people seem to be able to figure out 1K and above spectrum directivity already. Does AP deal with shaping and redirecting the LF vertical coverage? Also, is the length of the array limits to the lowest frequency that AP is going to affect this minimum frequency has to do with the latency limits of low frequency based on FIR filters?
Whoa,
and
boy.
what is
Okay.
that frequency in either case?
Okay, wow. This is a little bit down a rabbit hole that I don't want to get into right now. I'm going to give a quick answer, and then Mark, let's leave that question up for right now, and then let's come back to that at the end.
Definitely.
Because, boy, that's a doozy. So AP, array processing, does try to control low frequencies, but it maxes out at 100 hertz. Once it gets below 100 hertz, it doesn't try to do that, to try to control it. And it is a result of trying to minimize the latency that is incurred by the combination of FIR and IIR filters. I'm sure there's more into that, but I think I can give, that's a very, very short answer on what could be an entire class, and is an entire class. But let's put a pin in it, and let's come back to that towards the end.
Cool. Another question is, what would be the minimum amount of loudspeakers to have an acceptable low frequency pattern control in an array?
How low a frequency do you want to control is really the answer. It's how low a frequency do you want to control, and to what distance do you want to control it, and where is the array located? I mean, unfortunately there is no definitive answer on this. To steal from Pat Brown, or to borrow from Pat Brown at Senad Khan, it's sound. The answer is, it depends, always. Unfortunately, there's very little like, here is the answer. So sorry, I couldn't give you more specifics than that.
He had a follow-up asking, or saying 100 hertz and 125 hertz.
Yeah, unfortunately, again, curvature, distance, coverage area. Honestly, the best way to determine this is with an array calculator. We try to keep this session as neutral as possible, but DNB does have a pretty good array calculator. It's ArrayCalc. You can download it on our website, and you can simply look at the dispersion or the throw distance for given frequencies. I want to look at 100 hertz. I want to look at 125 hertz. You can see what that dispersion is like in either 3 dB or 6 dB increments, depending on how precise you want to be. And realistically, I mean, you could mathematically figure it out, but that is actually the fastest way. Anytime that if I have to figure out, like, hey, how I need 100 hertz, I need a lot of 100 hertz great distance away. It's like, okay, cool. Let me throw a bunch of cabinets in and see what actually happens given the shape of the room, the curvature of the array. So I would say, looking at what we just looked at today, probably more than 16 cabinets, but again, depending on your throw distance. And it looks like Mark did throw a link into the chat feed of a link to ArrayCalc. And there actually are some pretty good videos there to get you started with ArrayCalc and how to use some of the various tools that are in there. So.
Yep. All right, another question. Referencing the spacing between drivers, did I hear correct? You mentioned LF was within half or quarter, like HF.
It is going to be one for low frequency omnidirectional sources. The criteria we're looking at is 1/2 wavelength. So greater than half a wavelength, you get lobing. Less than half a wavelength, you get narrowing. So other ones.
Can you brief again regarding the waveguide of speaker with more splay angle and less splay angles? Yeah,
so again, more rule of thumb, more party trivia, if you go to those types of parties. Generally, if you have cabinets with small amounts of splay, say like up to 7 degrees, that wavefront is probably going to be flatter than cabinets that have greater amount of splay, say like 10 degrees or 14 degrees. Those tend to have more curvature because you get more curvature of the array. So you're going to have, want more curvature in your wavefront so that it interacts properly when you get to those wider splay angles. Again, rule of thumb, not a absolute rule. Every manufacturer is going to have different criteria based on what their end goals are for a particular product. We tapped out.
It looks like we're good. We did have somebody make a comment about SL Series has some tricks up its sleeves because it is cardioid.
SL Series is, to quote some friends, German voodoo magic. So, and again, there's also a session on SL Series taught by one of the folks, Dave Thomas, in it's tomorrow and Thursday. There may still be some spots left. I know that there was a lot of demand for that session, so that's great. All right, so we've talked about top line arrays and how we're dealing with high frequency, mid frequency, maybe a little bit of low frequency. Let's kind of turn this around a little bit and look at exclusively controlling low frequency energy, where we want to create directional low frequency arrays. So let's look at, like everything, we got to go back to the beginning. Let's look at a single sub. This is an omnidirectional sub. Generally, you get about 3 dB reduction towards the rear, and that is roughly a factor of the cabinet that's actually surrounding the driver. The cabinet's acting as a baffle, so there's not as much energy wrapping around. So generally about 3 dB. So omnidirectional sources, we have an idea how those work. And we also know very common deployments that we see, like left-right stacks. We often see this, it's not uncommon, where you will get lobing. And you can see that on the left-hand side of the screen. You get that nice power alley in the center, and then you get lobing off to the sides, and then even off to the 90 degrees off, 45. And then on the right-hand side, you can see the far field polars for 4 different octave bands, and you get this chrysanthemum flower-looking dispersion of lobes and troughs all happening at different frequencies, and it just gets messy really, really quickly. And we've seen dispersion like this before. We talked about it earlier. We had a question on it. And it has to do with the spacing between the drivers. Again, it's that center-to-center distance of half a wavelength. Greater than half a wavelength, you get lobing. Less than half a wavelength, and you get narrowing. So let's take a look at how this might work. So I'm going to take 2 subwoofers, and we're going to look just at 100 hertz. And I have them spaced 12 meters apart. So this is like 40 feet, roughly, for those who don't speak metric. You can see that this is, the SPL dispersion is just a mess. We don't even have a power alley in the center. However, if we were to shrink the distance between these 2 subs to the half wavelength point at 100 hertz, or 1.7 meters, then we start to get directionality. You get cancellation off to the sides, and you get nice strong addition towards the front and towards the rear. So in essence, this is how we're going to get pattern control with low frequency sources. Excuse me. All right, so why don't we take these same cabinets, spaced 1.7 meters apart, center to center, but we add more cabinets to it to fill that same 12-meter area that we were looking at before. In this case, we got each cabinet spaced 1.7 meters apart over a 12-meter outer center-to-center spacing. And now we have very strong pattern control towards the center. Very little energy off to the sides, lots of energy towards the front, lots of energy to the back. Cool. So, and if we look at the far field polar, you can see that again. It's very consistent. The lobes and troughs, I mean, you get some nastiness in here, but they're pretty consistent. But a lot of pattern control to the rear, a lot of pattern control to the front. So this forward firing energy is great. That's where our audience is. That's where our front of house engineer is. That's where we want sound. However, this energy off to the back, we may not actually want that. It's, you know, that's energy that's not for our audience. So that is potentially going towards and bouncing off walls that are behind these subs, or it's going up, and ultimately it's increasing the reverberant field of the room. So we're losing intelligibility, and that is totally the opposite of what we're trying to do in sound system design. We want to increase intelligibility completely. So we want to reduce that energy towards the rear. There's a lot of different ways to do this. Ultimately, they involve a cardioid deployment of subwoofers, be that with some type of array, a cardioid substack, or with individual cabinets that are inherently cardioid to start with. And that can significantly reduce the energy towards the rear of the subarray, minimizing energy on stage, again, reducing the reverberant field and increasing the intelligibility within the entire sound system. And you can see that in the far field polar plot. You can see that significant reduction towards the rear of that array. Yeah, you get a little bit of energy towards the back, but that's not really much to be really concerned about. Cool. But now we have pattern control in the horizontal, and we have pattern control to the rear. Now we need to disperse this energy, because the mix engineer is really, really happy. They're getting a great show. However, the people over here, not getting as good a show. So how do we improve that? We can do it in the same way, could do it in the same way that we did it with our line arrays. And we can simply add some splay between the different subs. Now we could and to create that splay, we simply have a distance offset to create this curvature, where, you know, the front of this array is at one distance, and the front of the sub here and the front sub here is a distance apart in order to widen out the coverage. So, and you can see that we've effectively widened that out. Cool. However, here's the catch. The distance between this sub here and this sub here, the fronts of those subs, is about 2.1 meters, probably about 7 feet. How many of you actually have 7 feet in front of your stage to very precisely place subs so you get the desired curvature, and you have the time to measure out and do the math? I would venture that most don't. I certainly don't. However, what is the difference between offsetting in distance and offsetting the subs in time? The answer is absolutely nothing. So we can, as an alternative to physically spacing them, we can line them up straight and then progressively add delay time as we move away from the center. So we have our center array, and then we simply add on delay as we move away from the center, creating a gradated virtual curvature to this array that allows us to get the coverage area that we need for the room and for a desired audience area. This has the benefit of it takes up minimal space. It's very easy to set up, and you can change it on the fly. Built into array calc, you simply put in the number of positions you have and the cover and the distance, center distance, the outer subs that you want to cover, and then put in the coverage area that you want. If you want to say, I want 40 degrees of horizontal coverage, cool. You put that in and it will figure out what the delay times need to be put onto the individual subs. And then you can change that. You can create multiple snapshots within array calc. So you can have, say, instead of 40 degrees, you can have 80 degrees. So you can have multiple variations, same array configuration, just changing delay time. Just so it depends, so that you can change dynamically based on where the audience is and what type of room you're in, if it's particularly reverberant. So, what questions do you guys have about subs? Horizontal sub arrays. Mark, what do we got?
We have a question. How delay between subs to do that arc, can align it in time with the main PA system?
Yes. So that is something you have to take into, or something that piece of software needs to take into consideration. Just like our flown arrays, our flown mid-high array, or mid-high arrays, we're trying to treat those as a complete unit. We're also going to do that for our subarray. And we're going to want to time align the entire array. In array calc, D&B's array prediction software, it will take your, if you're doing like a left-right array, which is pretty common, it'll take a measurement point on axis with that array and do a delay based on the phase interaction between the top and the sub array as a whole. And then you pick your point within the audience area where you want to measure to. Because remember, you can't have multiple delay times for everyone. So you have to figure out the point where you're going to get the best delay time for the most amount of people. And generally, a good place to pick that point is when you are a point where you're equidistant from your flown main array to your horizontal ground deployed array. That distance, if you're equidistant away, that is a good place to start thinking about this is where you're going to time your system to. And you do that in array calc, you'll see that as you move close to the front of the space and then towards the back, you'll see that you'll stay within that 90 degrees of phase difference. So you're getting that at least a 3 dB boost across the vast majority of the audience area. Now, when you get up close, the time gets off, but it becomes less of an issue because you're so close to the subs. People just don't care anymore. They won't be able to hear the difference because they're getting all their low energy from the stuff that's close to them. And at the back, it gets a little wonky because you're just far enough away that it happens. And you can compensate, again, having delay systems and delay subs, but that's a whole other level of complexity. So hopefully that answers your question, maybe a little bit more detailed than you needed, but there it is.
Another question is, can you create a line arc array with a mix of omni and cardioid subs, i.e. 2 B2 infras and 2 B sub outers?
No. I mean, yes, you could. Physically, you can mix them. However, array calc won't give you any, won't allow you to predict that. And the phase relationship between the cardioid subs and the omnidirectional subs are different enough that you're not going to get desirable outcomes. Particularly when you're talking about like the B2 and B22, because that's a dual bandpass design, that phase response is different than the majority of our other subs who are designed to be phase coherent at their crossover frequency with our top arrays. So In the real world, yes, you could do it, but there's no way to predict that behavior. So we highly recommend not doing it.
Okay. Another sub question: is spacing between subs recommended with Omni subs too, or is it just a cardioid sub rule?
I believe you're referring to in order to get the ideal cardioid behavior off a single sub or a sub stack, there is a criteria of you want at least 2 feet to the sides of the subs in order to maintain that cardioid behavior. That is not necessary for omnidirectional subs. Because it's not dependent, the behavior of the sub is not dependent on energy getting towards the back. We actually don't, when we're dealing with omnidirectional, we may not even care that the energy is back there. We just accept that it's there. So considerations to think about, but not in terms of like, you have to be very, very concerned. For a cardioid, you have to be aware of it. If you go less than 2 feet edge to edge, is it going to be problematic? No, you will get less ideal cardioid behavior, but I wouldn't stress about it. But I wouldn't put the cabinets butted right up next to each other. I'd go for as much as I could to get that 2 foot spacing between the cardioid subs. So hopefully that answers your question. Not add a follow up in there.
Another one, back to LF distancing. LF drivers and line arrays are still half or quarter. Is this half just floor level? Because quarter is 0.85 meters, of which we clearly meet in line arrays.
When we're dealing with, anytime we're dealing with low frequency drivers, omnidirectional drivers, it is going to be the criteria to get pattern control off multiple sources is 1/2 the wavelength. Doesn't matter when you're flying, if it's a flown thing or if it is a ground deployed thing. You will get a boost if you're ground deployed. If you're talking about horizontal subarray, you do get that ground coupling boost, but that doesn't really factor in when you're just talking about pattern control for the different drivers. We should keep in mind, that center to center criteria. Like, it's good for us to keep in mind, like, the back of our head, so we can know, like, oh, I should do this. ArrayCalc and many other subarray calculators will give you this information. Like, all you really need to put in is like, this is my available space, and it will tell you what your maximum frequency for pattern control is. At least in the case of ArrayCalc, it'll tell you, like, this array based on the spacing will control up to a particular frequency. And if it says, oh, well, I can control up to 150 hertz, you're like, great. I'm not going to be producing anything close to 150 hertz, so this is fine. Whereas if it says, oh, well, we have pattern control down to 60 hertz, it's like, ooh, maybe I need to either tighten up that subarray or add some additional sources so I can get that center to center distance down a bit, so I can control to a higher frequency. Because generally you probably want 100 hertz, max frequency pattern control, maybe 100 hertz, 120, depending on your content. So what else? Hopefully that answers your question. Again, follow up.
We had a question about the pattern control in subarray in ArrayCalc, so I think that might have answered that.
Okay, hopefully if it does answer the question, cool. If not, again, follow up.
Another thing worth noting, delaying subs will really affect the transient response. Plus, it's worth angling the outer cardioid subs to keep the lobe off the stage.
It can, absolutely. Because you're distributing energy that transient will be affected in some way. And you can turn subs outwards, so you can the outer subs you can, so you can widen things out, maybe minimize a little energy on stage. Again, all of this is visible in array calc, so you can see exactly what kind of dispersion you're getting. So cool. Other questions?
I think we're caught up.
Okay, great. Do we want to try and tackle this AP question? Oh, wait, maybe we don't have to go that far.
Just got another question
Okay.
in here. Don't you find the lack of polarity reverse in array calc R1 amps switch to a little bit annoying when it comes to reality?
Do you want the real answer, or do you want the snarky answer?
I want to hear both, but maybe the real answer.
I mean, it can be annoying. I guess it depends on your where you're getting your signal from, and how well that's maintained. I know that having the polarity reverse capability can enable you to more easily do things when trying to get subs and tops to couple together. D&B for the longest time has taken the stance that you should not have to do that with a properly designed system. That you can, it can be helpful, but you shouldn't necessarily have to do that. If the cabinets are designed to work together as a complete system, that shouldn't be necessary. Yeah, of course, when you you might start getting into more extremes, and that becomes a thing. And that's where you have you have a delay feature. And if I want to put on a sales guy hat, which I don't want to do, but there's also the DS100, which is a 64x64 cross-point matrix, which has polarity switches on the ins and the outs. So to compensate for the lack of polarity switches on any other product, we have put 128 of them into one box to screw you up 128 different ways. Or fix things 128 different ways, whichever way you want to do it. And the snarky answer to that is make sure your cables are wired properly. But again, snark rather than a real answer. So what other questions do we have in there?
That's it. So I think we can, good answer is a reply to that. So
okay, good. Okay,
good. Let's try to hit up this AP question. And then if anybody else has any other questions, feel free to keep putting them in and we'll keep answering as they come.
Yeah, absolutely. So if anyone, we're pretty much done with the session. We're just kind of, riffing at this point. So we're going to tackle this heck of a AP question, and then we'll probably call it a day. But if you want to hang out, great. Otherwise, if you can't hang out any longer, it was great having everyone here, and hopefully we'll see you in future webinars. So thanks for joining us. Really appreciate it. Okay, let's see if we can tackle this AP question here. Let me, Mark, can you remind me of what we're dealing with here? All right.
Yeah. So let's see here. So essentially AP is dealing with what the line array theory can't. Every manufacturer has managed to control the directivity of 1K hertz and above. The problem is with low and low mid directivity beaming, which is something that must be matched with super tight controlled HF beaming. Is this problem something that D&B's AP deals with? Shaping and redirecting the low frequency vertical coverage also as the length of the array limits the lowest frequency that AP is going to affect, or this minimum frequency has to do with the latency limits of low frequency based FIR filters, and what's the frequency in either case?
Yes. Okay, so I think for the most part I actually answered that with the when we really quickly reviewed that. So we have to keep in mind that array processing's goal overall is to make